Modes of data flows. At the beginning of this chapter, we said that whenever you want to send some data to another process with which you don't share memory, for example, whenever you want to send data over the network or write it to a file, you need to encode it as a sequence of bytes. We then discuss a variety of differences in coding for doing this. We talk about forward and backward compatibility, which are important for evolvability, making change easy by allowing you to upgrade different parts of your system independently and not having to change everything at once. Compatibility is relationship between one process that encodes the data and another process that decodes it. That's a fairly abstract idea. There are many ways data can flow from one process to another. Who encodes the data and who decodes it? In the rest of this chapter, we will explore some of the most common ways how data flows between processes. Via databases, see data flows through databases on page 129. Via service calls, see data flows through service, REST, and RPC on page 131. Via asynchronous message passing, see message passing data flows on page 136. Data flows through databases. In a database, the process that writes to the database encodes the data, and the process that reads from the database decodes it. There may just be a single process accessing the database, in which case the reader is simply a later version of the same process. In that case, you can think of storing something in the database and sending a message to your future self. Backward compatibility is clearly necessary here, otherwise your future self won't be able to decode what you previously wrote. In general, it's common for several different processes to be accessing a database at the same time. These processes might be several different applications or services, or they may simply be several instances of the same services, running in parallel for scalability or fault tolerance. Either way, in an environment where the application is changing, it is likely that some processes accessing the database will be running newer code and some will be running older code. For example, because a new version is currently being deployed in a rolling upgrade, so some instances have been updated while others haven't yet. This means that a value in the database may be written by a newer version of the code and subsequently read by an older version of the code that is still running. Thus, forward compatibility is also often required for databases. However, there is an additional snag. Say you add a field to a record schema and the newer code writes a value for that new field to the database. Subsequently, an older version of the code, which doesn't yet know about the new field, reads the record, updates it, and writes it back. In this situation, the desired behavior is usually for the old code to keep the new field intact, even though it couldn't be interpreted. The encoding format discussed previously supports such preservation of unknown fields, but sometimes you need to take care of an application level, as illustrated in a figure 4.7. For example, if you decode a database value into model objects in the application and later encode those model objects, the unknown field might be lost in the translation process. Solving this is not a hard problem. You just need to be aware of it. When another version of the application updates data previously written by a newer version of the application, data may be lost if you are not careful. Different values written at different times. A database generally allows any value to be updated at any time. This means that within a single database, you may have some values that were written 5 milliseconds ago and some values that were written 5 years ago. When you deploy a new version of your application or a server-side application at least, you may entirely replace the old version with the new version within a few minutes. The same is not true of databases content. The 5 years old data will still be there in the original encoding unless you have explicitly rewritten it since then. This observation is sometimes summed up as data of life code. Rewriting data into a new schema is certainly possible, but it's an expensive thing to do on a large dataset, so most databases avoid it if it's possible. Most relational databases allow simple schema changes, such as adding a new column with a null default value without rewriting existing data. When an old row is read, the database is filling null for any columns that are missing from the encoding data on disk, linking it document databases, Espresso use Avro for storage, allowing to use Avro schema evolution rules. The schema evolution thus allows the entire database to appear as if it was encoding with a single schema, even though the underlying storage may contain records encoding with various historical versions of the schema. Archival storage. Perhaps you take a snapshot of your database from time to time, say for backup purpose or for loading into a database warehouse. In this case, the data dump will typically be encoded using the latest schema, even if the original encoding in the source database contains a mixture of schema versions from different eras. Since you are copying the data anyway, you might as well encode the copy of the data consistently. As the data dump is written in one go and is thereafter immutable, formats like Avro object containers file are a good fit. This is also a good opportunity to encode the data in analytics-friendly column-oriented formats such as Parquet. See column compression on page 97. In chapter 10, we will talk more about using data in archival storage. Data flow through services, REST, and RPC. When you have processes that need to communicate over the network, there are a few different ways to arrange that communication. The most common arrangement is to have two roles, client and server. The server exposes an API over the network, and the client can connect to the server to make requests to the API. The API exposed by the server is known as a service. The web works this way. Clients, web browser, make requests to the web service, making GET requests to download HTML, CSS, JavaScript, image, etc., and making POST requests to submit the data to the server. The API consists of a standardized set of protocols and data formats, HTTP, URL, SSL, TLS, HTML, etc. Because web browsers, web servers, and website authors mostly agree on these standards, you can use any web browser to access any website, at least in theory. Web browsers are not the only type of client. For example, a native app running on a mobile device or a desktop computer can also make network requests to a server, and a client-side JavaScript application running inside a web browser can use XML HTTP requests to become an HTTP client. This technique is known as AJAX. In this case, the server response is typically not HTML for displaying to a human, but rather data in an encoding that is convenient for further processing by the client-side application code, such as JSON. Although HTTP may be used as the transport protocol, the API implemented on top of is application specified, and the client and server need to agree on the details of that API. Moreover, a server can itself be a client to another service. For example, a typical web app server acts as client to a database. This approach is often used to decompose a large application into smaller services by area of functionality, such that one service makes a request to another when it requires some functionality or data from that other services. This way of building application has traditionally been called a service-oriented application. More recently, refined and rebranded as microservices architecture. In some ways, services are similar to databases. They typically allow clients to submit and query data. However, while databases allow arbitrary queries using the query language we discussed in Chapter 2, services expose an application-specified API that only allows input and output that are predetermined by the business logic, application code of the service. This restriction provides a degree of encapsulations. Services can impose fine-grained restrictions on what client cannot and cannot do. A key design goal of a service-oriented microservice architecture is to make the application easier to change and maintain by making services independently deployable and evolvable. For example, each service should be owned by one team, and that team should be able to release new versions of the services frequently without having to coordinate with other teams. In other words, we should expect all a new version of server and client to be running at the same time. And so the data encoding used by servers and client must be compatible across versions of the services API, precisely what we have been talking about in this chapter. Web services. When HTTP is used as the underlying protocol for talking to the services, it is called a web service. This is perhaps a slight misnomer because web services are not only used on the web, but in several different contexts. For example, one, a client application running on a user device, example, a native app on a mobile device or a JavaScript web app using AJAX, making requests to a service over HTTP. These requests typically go over the public internet. One service making request to another service owned by the same organization, often located within the same data center as part of the service-oriented microservices architecture. Software that support this kind of case is sometimes called middleware. One service is making requests to a service owned by a different organization, usually via the internet. This is used for data exchange between different organizations' backend systems. This category includes public API provided by online services such as credit card processing system or OAuth for shared access to user data. There are two popular approaches to web services, REST and SOAP. They are almost diametrically opposed in terms of philosophy, and often the subject of heated debate among their respective proponents. REST is not a protocol, but rather the design philosophy that builds upon the principle of HTTP. It emphasizes simple data formats using URL for identifying resources and using HTTP feature for cache control, authentication, and content type negotiation. REST has been gaining popularity compared to SOAP, at least in the context of cross-organizational service integration, and is often associated with microservices. An API designed according to the principle of REST is called RESTful. By contrast, SOAP is an XML-based protocol for making network API requests, although it is more common use over HTTP. It's aimed to be independent from HTTP and avoid using most HTTP features. Instead, it comes with a sprawling and complex multitude of related standards. The Web Service Framework, known as WS, that add various features. The API of SOAP's web service is described using XML-based language called the Web Service Description Language, or WSDL. WSDL enables code generation so that a client can access a remote services using local classes and method calls, which are encoded to XML messages and decoded again by the framework. This is useful in statical type programming languages, but less so in dynamical type ones. The code generation in dynamical type languages on page 177, 127. As WSDL is not designed to be human readable, and SOAP messages are often too complex to construct manually. Users of SOAP rely heavily on tool supports, code generation, and IDEs. For users of programming languages that are not supported by SOAP vendors, integration with SOAP services is difficult. Even though SOAP and its various extensions are ostensibly standardized, interoperability between different vendors' implementation often causes problems. For all these reasons, although SOAP is still used in many large enterprises, it has fallen out of favor in most smaller companies. RESTful APIs tend to favor simpler approaches, typically involving less code generation and automated tooling. A definition format such as OpenAPI, also known as Swagger, can be used to describe RESTful APIs and produce documentation. The problem with remote procedural calls, RPC. Web services are merely the latest incarnation of a long line of technology for making API requests over the network, many of which receive a lot of hype but have serious problems. Enterprise Java Bean (AJB) and Java Remote Methods Invocation (RMI) are limited to Java. The distributed component object model (DCOM) is limited to Microsoft platform. The Common Object Request Broker Architecture (CORBA) is excessively complex and does not provide backward or forward compatibility. All these are based on the idea of remote procedural calls, which has been around since 1970. The RPC model tries to make a request to a remote network service look the same as calling a functional method in your programming languages within the same process. This abstraction is called location transparency. Although RPC seems convenient at first, the approach is fundamentally flawed. A network request is very different from a local function call. A local function call is predictable and either succeeds or fail, depending only on the parameters that are under your control. A network request is unpredictable. The request or response may be lost due to a network problem, or the remote machine may be slow or unavailable, and such problems are entirely outside of your control. Network problems are common, so you have to anticipate them. For example, by retrying a failure request. A local function can either return a result or throw an exception, and or never return because it goes into an infinite loop or process crashes. A network request has another possible outcome. It may return without result due to timeout. In that case, you simply don't know what happened. If you don't get a response from the remote services, you have no way of knowing whether the request go through or not. We discussed this issue in more details in chapter 8. If you retry a failed network request, it could happen that the requests are actually getting through and only the responses are getting lost. In the case, retrying will cause the action to be performed multiple times unless you build a mechanism for deduplication, idempotence, into the protocol. Local functions don't have this problem. We discussed idempotence in more details in chapter 11. Every time you call a local function, its normal takes about the same time to execute. A network request is much slower than a function call, and its latency is also widely variable. Also, good times. It may complete in less than a millisecond, but when the network is congested or the remote service is overloaded, it may take many seconds to do exactly the same thing. When you call a local function, you can efficiently pass its reference pointer to the object in local memory. When you make a network request, all those parameters needs to be encoded into a sequence of bytes that can be sent over the network. That's okay if the parameters are primitive like number or string, but quickly becomes problematic with large objects. The client and the services may be implemented in different programming languages, so the RPC framework must translate data types from one language into another. This can end up ugly since not a language have the same types. Recall JavaScript problem with number greater than 253, for example. See JSON, XML, and binary variants on page 114. This problem doesn't exist if a single process written in a single language. All these factors mean that there is no point trying to make a remote service look too much like a local object in your programming language, because it is fundamentally different thing. Part of the appeal of the REST is that it doesn't try to hide the fact that it's a network protocol, although this doesn't seem to stop people from bringing RPC libraries on top of REST. Current direction of RPC. Despite of this problem, RPC is not going away. Various RPC frameworks has been built on top of all the encoding mentioned in this chapter. For example, Thrift and Arrow comes with RPC support included. gRPC is an RPC implementation using protocol buffer. Finagle also uses Thrift, and REST.ly use JSON over HTTP. This new generation of RPC frameworks is more explicit about the fact that a remote request is different from a local function call. For example, Finagle and REST.ly use future promises to encapsulate asynchronous actions that may fail. Future also simplify situations where you need to make requests to multiple services in parallel and combine their results. gRPC supports streams, where a call consists of not just one request and one response, but a series of requests and responses over time. Some of these frameworks also provide service discovery, that is, allowing a client to find out at which IP address and port number it can find a particular service. We will return to this topic on request routing on page 214. Custom RPC protocols with a binary encoding format can achieve better performance than something like generic like JSON over REST. However, a RESTful API has other significant advantages. It is good for experimentation and debugging. You can simply make requests to it using a web browser or the command line tool core without any code generation or software installation. It is supported by all mainstream programming languages and platforms, and there is a vast ecosystem of tools available: servers, cache, load balancer, proxies, firewall, monitoring, debugging tool, testing tool, etc. For the rest For this reason, REST seems to be the predominant style for public APIs. The main focus of RPC frameworks is on requests between services owned by the same organization, typically with the same data center. Data encoding and evolution for RPC. For observability, it's important that RPC client and server can be changed and deployed independently compared to data flowing through databases. As described in the last section, we can make a simplified assumption in the case of data flow through services. It is reasonable to assume that all the servers will be updated first and all the clients second. Thus, you only need backward compatibility on requests and forward compatibility on responses. The backward and forward compatibility properties of an RPC scheme are inherited from whatever encoding it uses. Drift gRPC protocol buffer and Afro RPC can be evolved according to the compatibility rules of the respective encoding format. In SOAP, requests and responses are specified with XML schemas. These can be evolved, but there are some subtle pitfalls. RESTful APIs most commonly use JSON without formally specified schema for responses, and JSON or URIs encode request parameter for request. Adding optional request parameter and adding new field to response object are usually considered changes that maintain compatibility. Services compatibility is made harder by the fact that RPC is often used for communication across organization boundaries, so the provider of a service often has no control over its client and cannot force them to upgrade. Thus, compatibility needs to be maintained for a long time, perhaps indefinitely. If a compatibility breaking change is required, the service provider often ends up maintaining multiple versions of the service API side by side. There is no agreement on how API version should work, how a client can indicate which version of the API it wants to use. For RESTful APIs, common approaches are to use a version number in the URL or in the HTTP accept header. For services that use API keys to identify a particular client, another option is to store a client request API version on the server and to allow this version selection to update through a separate administrative interface. Message passing data flow. We have been looking at the different ways of encoding data flow from one process to another. So far, we have discussed REST and RPC, where one process sends a request over the network to another process and expects a response as quickly as possible. And databases, where one process writes encode data and another process reads it again sometime in the future. In this final section, we will briefly look at asynchronous message passing systems, which are somewhere between RPC and databases. They are similar to RPC in that a client's request, usually called a message, is delivered to another process with a slow latency. They are similar to databases in that the message is not sent via a direct network connection, but goes via an intermediary called a message broker, also called a message queue or message-oriented middleware, which store the message temporarily. Using a message broker has several advantages compared to the direct RPC. It can act as a buffer if the recipient is unavailable or overloaded, and thus improve system reliability. It can automatically redeliver a message to a process that has crashes and thus prevent messages from being lost. It avoids the sender needed to know the IP address and port number of the recipient, which is particularly useful in a cloud deployment where virtual machines often come and go. It allows one message to be sent to several recipients. It's logically decoupled the sender from the recipient. The sender just publishes messages and doesn't care who consumes them. However, a difference compared to RPC is that message passing communication is usually one way. A sender normally does expect to receive a reply to its messages. It is possible for a process to send a response, but this will usually be done on a separate channel. This communication pattern is asynchronous. The sender does wait for the message to be delivered, but simply sends it and then forgets about it. Message broker. In the past, the landscape of message brokers was dominated by commercial enterprise software from companies such as TIBCO, IBM, WebSphere, and WebMethod. More recently, open source implementations such as RabbitMQ, ActiveMQ, HornetQ, NATS, and Apache Kafka have been popular. We will compare them in more details in Chapter 11. The details delivery semantic vary by implementation and configuration, but in general, message brokers are used as follow: one process sends a message to a name queue or topic, and the broker ensures that the message is delivered to one or more consumer or subscriber to the queue or topic. There can be many producers and many consumers on the same topic. A topic provides only one-way data flow. However, a consumer may itself publish message to another topic, so you can chain them together, as well shall see in chapter 11, or to a reply queue that is consumed by the sender of the original message, allowing a request-response data flow similar to RPC. Message brokers typically don't enforce any particular data model. A message is just a sequence of bytes with some data. You can use it any decode, any encode format if the encoding is backward and forward compatibility. You have the greatest flexibility to change publisher and consumer independently and deploy them in any order. If a consumer republishes a message to another topic, you may need to be careful to preserve unknown fields to prevent the issue described previously in the context of databases. Figure 4.7. Distribute actors frameworks. The actor model is a programming model for concurrency in a single process, rather than dealing directly with threads and the association problem of race, condition looking, and deadlocks. Logic is encapsulated in actors. Each actor typically represents one client or entity. It may have some local state, which is not shared with any other actors, and it communicates with other actors by sending and receiving asynchronous messages. Message delivery is not guaranteed. In certain errors scenario, message will be lost. Since each actor processes only one message at a time, it doesn't need to worry about threads, and each actor can be scheduled independently by the framework. In distributed actor frameworks, this programming model is used to scale an application across multiple nodes. The same message passing mechanism is used no matter whether the sender and receiver are in the same node. If they are on different nodes, the message in transparent coding into a byte sequence, sent over the network, and the code on the other side. Location transparency works better in the actor model than in RPC because the actor model already assumes that the message may be lost. Even within a single process, although latency over the network is likely high than within the same process, there is less fundamental mismatch between local and remote communication when using the actor model. A distributed actor framework essentially integrates a message brokers and the actor programming model into a single framework. However, if you want to perform rolling upgrades of your actor-based application, you still have to worry about forward and backward compatibility. A message may be sent from a node running the new version to a node running the old version, and vice versa. Three popular distributed actor frameworks handle message encoding as follows. Aka uses Java's built-in serialization by default, which does not provide forward or backward compatibility. However, you can replace it with something like protocol buffers, and thus gain the ability to do rolling upgrades. Orleans, by default, uses a custom data encoding format that does not support rolling upgrade deployments. To deploy a new version of your application, you need to set up a new cluster. Move traffic from the older cluster to the new one and shut down the old one. Like with Aka, custom serialization plugins can be used. In Erlang OTP, it's surprisingly hard to make changes to record schema despite the system having many features designed for high availability. Rolling upgrades are possible but need to be planned carefully. And experimental new maps databases, a JSON-like structures introduced on Erlang R17 in 2014 may make this easy early in the future. Summary. In this chapter, we look at several ways of turning data in structures into bytes on the network of bytes on disk. We saw how the details of this encoding affects not only their efficiency, but more importantly, also the architecture application and your option for deploying them. In particular, many services need to support rolling upgrades, where a new version of a new service is gradually deployed to a few nodes at a time. Rather than deploying to a node simultaneously, rolling upgrades allow new versions of a service to be released without downtime. Thus, encourage frequent small releases over rare big releases and make deployment less risky, allowing faulty releases to be detected and rolling back before they affect a large number of users. These properties are hugely beneficial for evolvability. The ease of making change to an application. During rolling upgrades or for various other reasons, we must assume that different nodes are running the different version of our application code. Thus, it is important that all data flowing around the system is encoded in a way that provides backward compatibility. New code can read old data, and forward compatibility. Old code can read new data. We discussed several data encoding formats and their compatibility properties. Programming languages specific encoding are restricted to a single programming language and often fail to provide forward, and backward compatibility. Textual formats like JSON, XML, and CSV are widespread and their compatibility depends on how you use them. They have optional schema languages, which are sometimes helpful and sometimes hindrance. These formats are somewhat vague about data types, so you have to be careful with things like numbers and binary strings. Binary schema-driven format like Thread, Protocol Buffer, and Afro allow compat efficiently encoding with clearly defined forward and backward compatibility semantics. The schema can be useful for documentation and code generation in a statically typed language. However, they have the downside that data needs to be decoded before it's human readable. We also discussed several modes of data flows, illustrating different scenarios in which data encoding are important. Databases where the process reading to the database encoded data and the process reading from the database decoded, RPC and REST APIs, where the client encodes a request, the server decodes the request, and encodes a response, and the client finally decodes the response. Asynchronous messaging passing, using message broker or actors, where nodes communicate by sending each other messages that are encoded by the sender and decoded by the recipient. We can conclude that with a bit of care, backward-forward compatibility and rolling upgrades are quite achievable. May your application evolution be rapid and your deployment be frequent.